Welcome to qnawire.
We have another combination let's see here, gas cycle with the steam cycle. But now we have some inefficiencies in the compressor and the turbines. So basically just adding a little more complication to this. So now these aren't vertical lines. So we have some added entropy through the turbine, through the steam turbine, through the gas turbine, and through the um, compressor. Otherwise, everything is pretty much the same as the previous problem. So a lot of this stuff is the same. In fact, well, this is all the same. But then we can get the enthalpy at the what do you call it? The at state 9 for the isentropic case. So that would be straight up here. And then knowing the efficiency of the compressor, we can get the actual enthalpy at 9. So then, again, knowing the temperature at 10, we can get the enthalpy and the reduced pressure. And again, knowing the pressure ratio, we can get the reduced pressure at 11, which gives us the isentropic enthalpy at 11. Which then we can use the efficiency of the turbine to get the actual enthalpy at 11. And again, knowing the temperature at 12, which was just as before, we can get the enthalpy at 12. And again, going on to the pump and to the steam side, all of this stuff is the same, I think. Is that all the same? Yeah, that's all the same. All this pump stuff is the same. This is the same. This is different because now we have an isentropic quality factor and an isentropic enthalpy, but we know the efficiency, so we can get the actual enthalpy at 6. And likewise, we can at 7, we know that in the isentropic case, the isentropic entropy is the same as that at 5. So we can get the isentropic quality factor, the isentropic enthalpy, and then from knowing that and the efficiency, we can get the actual enthalpy at 7. And so again, we have all of the enthalpies we need to just start doing our analysis here. So again, we can get do an energy balance on the heat exchanger, or basically the combination condenser boiler thing. So we got at the heat exchanger, we get a ratio of mass flow rates. And in this time now, it's 6.425 kilograms of air per kilogram of steam. Before it was up at 9, so we've changed things quite a bit. Same thing here on the feed water heater energy balance. And then so now we're bleeding off about 17.35% of the steam from the turbine, as opposed to, where was this before? 17.92. So a little less. Then we can go on and get the specific work in the turbine and the steam side, and I just used let's see here. I think should those be primes? Let me check my notes again. Let's see here. What problem were you on? 80, I think. Let's see here. Problem 80. Yeah, down here. Let's see here. 6. Let's see here. Did we use? I'm not sure why. Let's see here. H5. Let's see here. Yeah, I'm not sure why. I don't think I should have this in there because I've already used the efficiency to get these these values here, or these values here should be the isentropic values, because if we're isentropic values, then I think these are, these should be the isentropic values. Yeah, that's what I did in my notes. Yeah, I'm just trying to check what numbers I used in here. Yeah. So these should be either isentropic values or the non-isentropic values, and then without this here. So in the end, we wind up with this a work output here of 824.5 kilojoules per kilogram, specific work out of the steam turbine. The net work out of the steam turbine, again, we gotta, not all of the flow is going through the pump 1, all of it is going through pump 2. So we, prorate this, and so this is per kilogram of steam going through the turbine. So we have 815.9 kilojoules per kilogram of steam going into the turbine. And then the net work in the gas cycle, again, the work out of the turbine minus the work into the compressor, or the, and that winds up being 261.6 kilojoules per kilogram of air. And so now if we want a net work of the whole thing and we want to get it on a kilogram of air basis, so we need to then convert this from kilograms of steam to kilograms of air, but we know that conversion factor. And so we get 388.6 kilojoules per kilogram of air. And now we know we were given this as before. That was what was it, 450 megawatts. And so we now, I'm not sure why I put a dot on my specific work down there. So that's just all right. So then we know this. We were given that 450. That equals 450 megawatts, and then dividing it by this guy, we get 1,158.2 kilograms of air per second. And now we can figure out the heat flow into the turbine, or into basically the combustion process. The energy got out of the combustion process is heat, and that's almost close to a terawatt. So 934 megawatts. And well, we can get the efficiency now because we just take this and we divide it by this, and we get 48.2%. And that's actually quite a bit less than what we had here, 62.5%, because we had losses in our turbines and our compressor. Doesn't seem like a lot, but it actually dropped the percentage, the overall the overall efficiency of the whole process down quite a bit, from what was it, 62.5 down to 48.2.